This is also marking the kickoff for, I'm sorry, I'm trying to admit people as well, for discussions in one of the theme, the explainability theme, which, as you probably know, is a central concern to IRIT. And Martin Cooper, who is a member of IRIT and a professor at Université Paul Sabatier, and was very well known in the field of automated reasoning. We'll be giving a talk on tractable explaining, and we're very happy that you can do this for us, Martin. Thank you so much and welcome.
Okay, well, thank you, Nicolas. And so I'm giving the talk in English because I'm making that great sacrifice to talk in my mother tongue, because this is a paper we've just submitted to IRIT, and if it gets accepted, obviously, I will have to give a talk in English. So the title is Tractable Explaining. I'll explain the word explaining later, because it does need some explaining. Tractable just means what can we solve in polynomial time. Okay, so so an outline of this talk is, first of all, we're explaining what? We're explaining decisions taken by a classifier. And so, first of all, we have to understand, we have to decide what constitutes an explanation of a decision. So we'll be giving two different definitions, but basically based on the idea of a subset of the features which justify a decision. So the main question we're asking ourselves is, for which classifiers can explanations be produced in polynomial time? So clearly, if you usually a classifier goes without saying that the result, the prediction, is produced in polynomial time. It's fast. We would also like to be able to produce an explanation of a prediction or a decision in equally efficiently. So after we've answered that question, we'll ask more technical questions of what happens if there are constraints on the possible data. Does this change the tractable classes? An interesting point that we'll talk about is, are the tractable classes identical for explaining positive and negative decisions? Clearly, you may want to have an explanation of a positive decision or a negative decision, and do we get the same tractable classes? And that's one of the results here, which I'll talk about. Obviously, at the end will be discussion. So let's get the basic definitions out of the way. So we consider a classifier in this talk to be a Boolean function. We take a vector of features, x, which may involve, for example, if it's a person, their salary, their age, their gender, their nationality, whatever. And we want to make a decision, and so the classifier returns either 0 or 1. It says either no or yes. So examples are, for example, should a bank approve a loan to a customer? Should a student be admitted to a course? Or, more seriously, is this tumor malignant? So clearly there are many possible applications. We will give examples in this talk concerning the bank approving a loan to a customer, but clearly it could be any classifier. So just to get things straight about the words I'm using. So a data set is a set of tuples. So there are examples or instances. And machine learning is the problem of, given a data set, produce a model. So we're not interested in machine learning today. I mean, we assume that machine learning has already been done, and that what we're interested in is explaining. In other words, we have a model already. We have some data, in other words, one vector, which we call A, and that gives a decision C. So the model we call tau. Tau A gives C. And what we want is an explanation. So for us, an explanation will be a subset of the features which accounts for that decision. Okay, we'll see what that means technically as we go on. So first definition of an explanation is an abductive explanation. So suppose that a classifier, suppose that tau is a classifier with n arguments. So for simplicity, we will name these arguments of features from 1 to n. And we consider a feature vector A, which returns a value C. So an abductive explanation, also known as a prime implicant explanation, is what could be called a prime implicant of this decision. It's a minimal subset of the features, P, which the formula is maybe not easy to read, but basically it says that any feature vector which agrees with A on the features in P will also be classified as C by the classifier tau. So in other words, the set P is the set of features which guarantee we will always have the same decision. So that's the basic definition we'll be using in the first half of the talk. An abductive explanation is simply a subset of the features which, if these are assigned the same as in A, then whatever values we assign to the other features, we will still get the same decision. Okay, so let's look at a very simple example. So suppose that a bank uses a function tau to decide whether to grant a loan to a couple. So here, for simplicity, a couple is represented by a feature vector, salary 1, salary 2, age 1, age 2. So the two people in the couple, we're just looking at their salaries and their ages. Now, suppose that tau returns 1, if and only if one of the people earns more than a minimum salary, S min. So the maximum of the salaries is greater than or equal to S min. And at least one of the people is sufficiently young. In other words, the minimum of the two ages is less than or equal to the maximum age, A max. So this is a plausible, if simplistic, model that a bank could use. They don't, as they say in French, we only lend to rich people. And according to this criteria, you wouldn't want to give a 30-year loan to someone who was already 100 years old, for example. There's obviously some limit to the age. So we're using this as an example to illustrate what an abductive explanation is. So suppose A is a couple who both earn more than the minimum salary and who are both younger than the maximum age. Then there are lots of explanations why this couple is given the loan. For example, 1 free is an abductive explanation. In other words, the first and third features, salary 1 and age 1, are sufficient to explain the decision. If the man gets divorced and marries a much older woman who has no job, it's still good, he can still get the loan. Okay. Similarly, there are 4 abductive explanations because 1 4 is an abductive explanation, as is 2 3 or 2 4. So perhaps more interesting case is the case of a couple who is refused a loan, because if you get a loan, you're not going to go back to the bank explaining angrily, asking angrily, why did you give me this loan? No, it's more the couple who is refused the loan who is going to ask for an explanation. So B is a couple who got refused. Why? They both earn more than S min, but both are old. Both are older than A max. So according to this function tau, they are refused. Now, the only abductive explanation for the decision of refusal is free for. In other words, the two features, H1 and H2. In other words, they are both too old. If they keep the same age, but they change their salary, it doesn't help. Okay, any combination with the same ages would still have the same decision. So we can see this obviously is the reason why they were refused. They were both too old. Okay, but the first example with A, where there were 4 abductive explanations, shows you that in the worst case, we can have an exponential number of abductive explanations. In this example, you can see we have all combinations of the salaries and ages. So we can obviously generalize this to, for example, if you have a majority vote, you just need to have n over 2 Boolean variables true to have something approved. If someone ticks all the boxes, has all those variables true, then the number of abductive explanations is the number of ways of choosing n over 2 objects from n. So it's a very large number. So that's why we're interested in just finding one explanation rather than finding all explanations. So when we talk about tractability, it will be of the problem of finding one abductive explanation. Now, we're going to be just looking at threshold classifiers. So what is a threshold classifier? So we say that tau is a threshold classifier if for some real valued objective function f and some real constant t, the threshold, tau x returns 1, if and only if fx is greater than the threshold t. So we'll be looking at, we've done this, we're restricting ourselves to threshold classifiers because we know about classes of functions which can be optimized in polynomial time. So for example, if we look at the set of linear functions, then the corresponding set of classifiers are linear classifiers. We're just asking, is a linear function of the features greater than some threshold? For example, this is the case in naive Bayes classifiers. Linear is a very restrictive condition. We will be looking at other conditions on the function f, which will lead to tractable explain. Now, in fact, this is not actually a restriction to look at threshold classifiers because truthfully, any Boolean classifier can be considered as a threshold classifier. The function tau itself, you just need to say, if it's greater than 0, then I'm saying yes. So we could just use tau as the function f. So it's not actually a restriction to look at threshold classifiers, but it does open up, it shows the links with related work in optimization problems and tractability of optimization, as we'll see later. So we're interested in classes of functions, this famous objective function f. So we will place restrictions on f, otherwise the problem is not tractable. So what kind of restrictions can we place on f? So one restriction is that f is monotone. Now, monotone means that if you increase any number of the components, any number of the features, then the value of f increases. So we have an equivalent definition, antitone, if on the right-hand side you have greater than or equal to, and otherwise increasing the features decreases f. For example, imagine a student who is applying for a course. He's going to fill in a CV and send it off. Generally on your CV, you only put positive things. So in this case, we can expect the function f to be monotone. The higher the marks of the student, the more likely we are to accept him. So monotonicity is a fairly easy concept to understand. And we can see that very easily that certain classifiers will have this property. Another interesting property is submodularity. Now, submodularity is a well-known property in operations research, machine learning, image processing, but perhaps not all of you have seen it before. So a function f is submodular if for any two vectors x and y, if we now consider two new vectors which we obtain by taking first the minimum component y's of x and y, and secondly the maximum component y's of x and y, then these two new features, when you sum up their values of f, is less than or equal to the sum of the original values of f on x and y. Now, this is not a particularly natural, not as natural definition as monotonicity. But submodularity turns out to be very important in optimization problems. The notion of submodularity can be traced back to Gaspard Monge, a French mathematician who is perhaps not as well known as he should be. The next time you go to Paris and you look at the Eiffel Tower, look around the first floor of the Eiffel Tower. There are 72 names of famous French scientists, such as Fourier and Ampère, and you'll find Monge there as well. So at that time, he was quite well known. It's less well known now, but he invented, I don't think he called it submodularity, but he invented this concept, which is now known as submodularity. So what kinds of functions have these properties? That's what all linear functions are submodular, for example, but only those linear functions whose coefficients are non-negative are monotone. And all quadratic functions with negative coefficients of degree 2 terms are submodular. So that gives you a very large range of submodular functions. There are also other submodular functions. Okay, so let's have a look at another example. So we've gone now to a different bank and we're asking for a loan. So in this bank, they use a different function. And again, they use the same features, 2 salaries and 2 ages of the couple. But suppose now that tau is the following threshold classifier, where they use a sum, a weighted sum of 3 functions, f1, f2, and f3. And we see if the sum is greater than some threshold t. Now, the first function, f1, just takes into account the salaries. And this, I believe, is quite close to what banks actually do. They take the maximum salary of the couple, and if you're lucky, they have a value of mu which is non-zero, and they take into account the second salary. But often, they just take into account the maximum of the 2 salaries. But anyway, we'll have the general case where you'll have the maximum of the 2 salaries plus some constant mu times the minimum of salaries. And the function f2 is a function which wants to give an advantage to people who are not too young. You don't want both members of the couple to be under 18, obviously, or whatever. So you want the maximum of the 2 ages to be greater than some minimum age. The third function, f3, takes into account age, but really for old people, you don't want to be giving a loan, especially over a long period of time, to people who are very old for very obvious reasons. So you want to give a plus to people who, the couples for which the minimum age is less than or equal to the maximum age, A max. Okay, so this is a whole family of classifiers depending on the values give to mu, alpha, beta, gamma. Now, in fact, I won't prove it, but I have checked it. F1, F2, F3 are all submodular. So since submodularity satisfies additivity, the weighted sum is also submodular. So F is submodular. However, since F1 and F2 are monotone, but F3 is not, F is monotone only if the coefficient gamma is 0. We can see that straight away, the monotonicity, because it's obviously a good thing to have a higher salary. It's obviously, as far as F2 is concerned, it's a good thing to be older, but for F3, it's not a good thing to be older. Okay, that's the proof of submodularity for one of the particular cases at F1. I will skip that, don't worry. Okay, so I hope you'll take my word for it, but I did check, and those functions are submodular. Anyway, we are interested in families of classifiers, and we need a technical property which will be almost always true, but I need to state it. Given a classifier, we can consider, well, let's consider tau as just a function. So we can consider the function tau I u to be the classifier on n-1 features in which we fixed the ith argument to be u. So we're just looking at the sub classifier, which only concerns people whose ith feature is exactly equal to u. So we say that our family of functions is closed under fixing arguments if for any tau in this class, then any such function we obtain by fixing an argument is also in the class. This is true for all the classes we will be looking at: linear, monotone, antitone, submodular, supermodular. Any interesting class certainly satisfies this. So it's just a technical detail. Okay, so the main property which will be able to, which will justify tractable explaining, is the fact that this problem called tautology is tractable. So for a family of Boolean functions, let tautology t be the following decision function. For any function in t, is it true that t is a tautology? In other words, does it always return 1? Now, in the general case, assuming quite reasonably that all functions in t execute in polynomial time, tautology t is in co-NP. Quite simply, since a counterexample can be verified in polynomial time. So co-NP is not good if we're co-NP complete. That would mean that we're probably going to have an exponential time complexity. So we're interested in sub-classes where families of Boolean functions for which tautology would be in P. So it turns out that if T is closed under fixing arguments and tautology is solvable in polynomial time, then for any classifier in this class of classifiers and any positively classified input A, an abductive explanation of tau A equal to 1 can be found in polynomial time. So that's our first result. Now, this is fairly easy to prove because we just need a simple greedy algorithm. We start off, remember that we're looking for a subset, minimal subset of the features which justify the decision. So we start off with P, our possible explanation, as all the features, and then we just try and get rid of each feature. So for each feature, we ask, is P still a valid explanation when we get rid of the feature I? So here, valid explanation is just that the function we obtain by fixing the arguments in the subset P to be the same as in A, is that function a tautology? Does it always return the value 1? So we can see already the link, the immediate link with tautology, and why that the fact that tautology is solvable in polynomial time gives us immediately a polynomial time algorithm to find an abductive explanation. So we only need to apply to call to a tautology test n times, and we will find necessarily an abductive explanation. If we examine the features in different orders, we will get possibly different abductive explanations, but we're just looking at the question of finding 1. Okay, so now to get back to the assumption we made that our classifiers were threshold classifiers. In other words, we return a positive decision if and only if some function f of the features is greater than a threshold. So in that case, what does tautology mean? Tautology is tau always equal to 1 is the same as asking, is the minimum value of f greater than t? So clearly, we've reduced the problem of tautology to the problem of minimizing a function. So it turns out that if T is a set of threshold classifiers closed under fixed arguments, then tautology is in P if and only if functions can be minimized in polynomial time. I think that's fairly obvious from the previous line. So examples of classes of functions that can be minimized in polynomial time are monotone functions. The algorithm is simple. You take the minimum value in each domain. Submodular functions over finite ordered domains. Here, the algorithm is certainly not obvious, but there are polynomial time algorithms to minimize submodular functions. Just a little aside, you remember the very first example of a classifier, the first bank, used what we could call a multi-threshold classifier because there was an and, was a conjunction of two conditions. So what happens if you, in fact, have multiple thresholds? If to get the loan, you have to satisfy different criteria based on, for example, salary, age, etc. And these are joined as a conjunction rather than as a sum. Well, in this case, again, we can use the same argument. So suppose that you have a multi-threshold classifier of the form tau x is 1 if and only if each f applied to x returns a value greater than some threshold ti. Then the tautology question is tau a tautology is simply is the minimum value fi greater than ti for each I. So again, for the set of multi-threshold classifiers, we've reduced the problem of testing a tautology to the problem of minimizing functions. So this means we can mix and match classes of functions. For example, let's suppose a bank applies a criteria on salary and another criteria on age, and then does a conjunction. If the first function applied to salary is monotone and the second function applied to age is submodular, then that works. Okay, we could have all kinds of combinations. I will now go back to the single threshold case because it's just simpler to talk about, but whatever I say from now on does also apply to multi-threshold classifiers. So I haven't emphasized it, but what I said up to now is only valid for positive decisions. Now remember the bank example. We don't really want an explanation. If we get approved a loan, we're not going to go and complain to the bank. Oh, you gave me a loan, I need to have an explanation of that. No, it's the negative decisions which we're going to want explaining. Of course, in other situations, it could be both. If you get diagnosed as with cancer, you want to know why this positive decision was made, and perhaps if you got a negative diagnosis, then later you developed a cancer, you want to go back and ask, why did you give me that negative decision? So we can easily think of applications where we want both positive and negative explanations of both positive and negative decisions. Okay, so let's look at negative decisions. Now, everything is going to be similar, but strangely not quite the same. For example, where we had tautology, now we're looking at unsat. Because now the question is not to determine whether the classifier is a tautology, but whether it's unsatisfiable. In other words, we want to know whether the Boolean function tau is always equal to 0 rather than always equal to 1. So here we have, by a similar argument to what we've seen before, that for a class of threshold classifiers closed under fixing arguments, if unsat can be solved in polynomial time, then for any classifier, any negatively classified input can be explained in polynomial time. So for an abductive explanation of a negative decision, we need to be able to solve in polynomial time, unsat or of on tautology. Now these problems look very, very similar, but they are very different. For example, if the classifier was a DNF, which is not an unreasonable possibility, then tautology is a very difficult problem. It's co-NP complete. But unsat is trivial. So you can see these problems are very closely, very similar, but can have completely different complexities. And we'll see that now when we make the link with threshold classifiers. So we're going back to our threshold classifiers, which return a positive decision, one if and only if some function f of the features is greater than a threshold. So now the question we're asking when we're looking for an abductive explanation of a negative decision is the classifier unsat, is it always equal to 0? And now tau is always equal to 0 if and only if the maximum value of f is less than or equal to t, the threshold. So unsat can be solved in polynomial time if and only if the corresponding functions in f can be maximized in polynomial time. Now, anybody who's looked at these optimization problems will know that minimizing and maximizing is not the same thing. So examples of functions that can be maximized in polynomial time are linear or monotone functions. So there we find the same functions we had in the case of minimization, but submodular functions cannot be maximized in polynomial time. In fact, it's supramodular functions, which are simply, if f is a submodular function, then minus f is a supramodular function. So we get a different classes of functions which can be maximized in polynomial time. There is some overlap, but it's not the same functions which can be maximized or minimized. So, as is said in red, thus explaining a positive decision may be tractable, whereas explaining a negative decision may be intractable, and vice versa. So if you have your threshold function f, which is submodular, for example, you can explain very quickly positive decisions, but you will have difficulty explaining quickly negative decisions. So this is very surprising that we have this asymmetry between positive and negative decisions. On the other hand, if you have a monotone function f, then we can explain positive and negative decisions in polynomial time. So that's good. Okay, so that's the first main surprise, I think, was that we had different tractable classes for positive and negative decisions. Now we're going to look at a bit more sophisticated classifiers. We call these constrained classifiers because, in fact, in reality, not all combinations of features are possible. So, very simple example. So, consider a medicine that doctors are allowed to prescribe to everybody who has a flu, except to pregnant women. I'm sure you see this written on almost every medicine that you buy, not to be given to pregnant women. Okay. There's something a little bit redundant in that because, as far as I know, there are no pregnant men. But of course, you don't save ink by putting pregnant people instead of pregnant women. But if Alice, who is pregnant, by the way, if she asks her doctor why he didn't prescribe her this medicine, he will say, oh, it's because you're pregnant. He will not say, it's because you're a pregnant woman. Okay, so this means that concretely, if we're returning an explanation, if you have constraints, which mean that not all combinations of features are possible, then your explanation can be more compact. You may give a shorter explanation. So that's one thing to bear in mind. Now, in the second example, it's kind of, we're trying to get round the problem that we had before. So this is the second bank. Now remember, the second bank had a rather complex function, which was f1 plus f2 plus f3. And the linear combination of these three functions was not monotone. Okay, it turned out to be some modular, but supposedly wanted a function to be monotone. Well, you could make f3 monotone by simply replacing age by the negative age, if you like, the number of years to retirement, which is basically, for example, 67 minus age, if we consider that 67 is the age of retirement. Now, if you do this introduction of new features, years to retirement, then suddenly your function f3 becomes monotone in these new features. So it looks like you've got over the problem. You've got now a function which is monotone, but you can't really do this. You're cheating unless you also introduce the constraint, which is that years to retirement equals 67 minus age. And so it shows you that when we're talking about tractable classes, the conditions we're putting on the function, we also have to put conditions on the constraints, because otherwise you could hide all the bad properties of your functions within the constraints. So we're going to see this later, but in fact, the tractable classes will now depend on what type of function you're trying to optimize and what type of constraints you have. So we have to give a formal definition of what an abductive explanation is if you have constraints. So let's suppose we have constraints C on our feature vector X. Well, quite simply, the definition is the same, except that it only applies to those X for which C is true. So we don't care what happens to V over X because they're not possible. Okay, we don't care what the classifier would, how the classifier would perform if we had a pregnant man, because there are no pregnant men. So it turns out that using the very simple logical equivalence at the bottom of the page, we can turn this round and put, instead of having C on the left, we can put it on the right. And we're looking at an abductive explanation of a classifier tau under constraint C is the same thing as an abductive explanation of the unconstrained classifier tau or not C. It's as if you don't satisfy the constraints, that immediately gives you the decision you want. Okay, so that just means that we can reduce to the non-constrained case very easily. So in the case of threshold classifiers, remember our classifier is now whether a function f is greater than a threshold. Well, to take into account the constraints, we can just introduce a new function g, which is 0 if the constraints are satisfied and infinity otherwise. And then we can look for an abductive explanation of f plus g. So f plus g will definitely be greater than t if g is equal to infinity. And we really only have to justify the other cases. Okay, so we now can go back and do exactly the same thing. We need now f plus g to have certain properties such as monotonicity, submodularity, etc. And we'll fall in a tractable class. So this gives us this table of tractable classes. So if we just look at the first 3 lines, where we're just talking about positive decisions. So I've mentioned that submodular functions, monotone functions, and clearly antitone functions give you a tractable class. If you can minimize any of these classes of functions in polynomial time. So if you have constraints as well, what properties do these constraints have to be such that the sum f plus g is submodular or monotone, etc.? Well, it turns out that the constraints have to be either max or min closed or both. So what does that mean? Max closed simply means that if x and y both satisfy a constraint, then if you take the maximum of x and y, the two vectors, then that new vector must satisfy the constraint as well. Min closed has the same parallel definition. Now that's not, if you've never seen this concept before, it's not quite clear what functions should be max closed, but just to give you an example of a max closed constraint, xi greater than or equal to xj, for example, is max closed. So this is a constraint which could occur if xi is the age, for example, and xj is the number of years you've worked. Clearly, your age is greater than the number of years you've worked. So this is a constraint we might want to apply, and fortunately that ticks all the boxes. It's max and min closed. Another example, I'm not going to prove it, but xi less than some constant or xj greater than some constant is another example of a max and min closed constraint. This means, for example, in the pregnant men example, you could, provided you choose the right orders on your features, you will have your constraint for no pregnant men is a max and min closed constraint. So you have to say that it's better to be pregnant and it's better to be a woman. And then you satisfy, then you are both max and min closed. I could have inverted it, that would be politically incorrect to say that it's better not to be pregnant and better to be a man. That works as well, but you mustn't have it's better to be pregnant and better to be a man. Then it wouldn't work. But if you've got the right orders on the domains, then that function of having no pregnant men will be both max and min closed. Okay, so as we've seen before, negative and positive decisions don't give the same classes, and we saw that with submodular and supermodular. And interestingly, also with the monotone functions, we saw that monotone worked for positive or negative decisions, but if you have constraints, they have to be min closed in a positive case and max closed in a negative case. So if you want to have both of these tractable, then you have to have your constraints both max and min closed. Okay, so that's just to emphasize again the difference between positive and negative decisions. And we've seen that we can have constraints on our classifier and that can still give us tractable classes. Okay, so that closes that chapter. Now, another chapter is a different kind of explanation. So I've spent all this time talking about abductive explanations. Now I'm going to talk about another kind of explanation, contrastive explanations. So we can basically say that abductive explanations answer the why question. Why did you make that decision? Whereas contrastive explanations answer the why not question. Why didn't you make a different decision? So our formal definition of a contrastive explanation is a set of features which, if changed in our vector A, can lead to a change of class. So this is different to abductive in the sense that we have, if you look at the formula at the bottom, we have an existential quantifier rather than a the for all quantifier. So it means that there is some assignment to the other features, not in our constructive explanation, which would allow us to change the decision. There are very interesting relationships between abductive and contrastive explanations. Given any subset of the features, either the some subset S, either a subset of S is an abductive explanation, or a subset of the complement of S is a contrastive explanation. There is also an interesting hitting set duality between contrastive and abductive explanations. These are things that Zhao has recently discovered, and not in this paper, but they're in another paper. Anyway, these are all very interesting facts, but for the moment, we're interested in the tractability of finding a contrastive explanation. So we saw the rather nasty surprise that positive and negative decisions don't have the same tractable classes. So what about abductive and contrastive explanations? Well, first of all, let's look at just an example to make sure we understand what a contrastive explanation is. So here we come back to the first bank. Remember, they had a classifier to decide on whether they should give a loan, which was that the maximum salary of the two people should be greater than S min, and the minimum age should be less than or equal to A max. So if we go back to the same two couples, the first couple, A, was they satisfied everything. They both, man and wife, earned more than S min, and both were younger than A max. So we're asking the question, what would they have to change the decision? So for example, 1, 2 is a contractive explanation. If they both lose their jobs, or they both have a great reduction in salary, then they will no longer be able to have the loan. Okay, so that's what a contrastive explanation means in this case. Another one would be that the is 3, 4. If they wait too long and they get older, then they're both too old, then that would be another reason for the decision to change. So here there are two contrastive explanations, 1, 2, and 3, 4. 1, 2 being salary 1, salary 2, and 3, 4 being age 1, age 2. So if B is the other couple, remember, who both earn a good salary, but both are old. So they're interested in changing their decision. They would like to know what they have to do to get a positive decision. Well, here a contrastive explanation is just 3, for example, or just 4. So if the husband had been younger, then they would have got the loan, because one of the members of a couple would have been young enough. So the wife has to divorce and marry someone younger to get the loan. That's the take-home message here. It's not a very good example, but you can imagine other examples where a student wants to know what he has to do to get admitted to a course. He has to do better in database course or whatever. Okay, so now we know what contrastive explanations are. And I go straight to the result about tractable classes. They are in fact exactly the same as for abductive explanations. So surprisingly, and that was quite a relief, that abductive and contrastive explanations have the same complexity. If we're in a tractable class for abductive explanations, then it's tractable for contrastive explanations, and vice versa. So we have, for example, the same table of tractable classes, with again the same problem that positive and negative decisions do not have necessarily the same complexity. So to finish, I will give a more theoretical take on all this work. And so we've seen that we've identified some tractable classes. Can we identify all tractable classes? So is there a dichotomy of threshold classifiers, those for which it's tractable to give an explanation, and those for which it's not, with the usual P not equal to NP supposition? So the answer is yes and no. If we make some more assumptions, then there is a dichotomy. So we're going to make an assumption that we're only looking at threshold classifiers which can be decomposed into a sum of smaller functions, f1 up to fm, where each fi has, we would imagine, a small scope. Now, in all the examples we've seen, this is what the functions look like. We had, for example, a function which looked at the two salaries, another one which looked at the two ages, etc. The interaction between the features is on a relatively local level. For example, two or three features at the same time. In this kind of decision-making process, we will not expect a global function which is some horrible mathematical function of all the features. Unfortunately, with neural networks, that's what you get. You get some horrible function mathematically, you get some horrible function of all the features. So this is not directly applied to such classifiers. But all the other types of classifiers would fall in this category. Okay, so consider the function CFNL. So CFN comes from a cost function network, which is equivalent to valued constraint satisfaction problems, which is more or less the same as weighted constraint satisfaction problems. So these are the problems of optimizing a global objective function, which is a sum of functions taken from a given language. So our theorem says that if L is a set of non-negative functions, because in the CFN framework, we only deal with non-negative functions. That's not really a restriction. You can always add a constant to make negative functions non-negative. And we assume these functions are closed under fixing arguments. Again, it's not really a restriction. Then finding one abductive or contrastive explanation of a positive decision of a classifier is tractable, if and only if CFNL is tractable. So we are basically saying if we can minimize functions in polynomial time, then we can find explanation of positive decisions. There is an equivalent theorem for negative decisions where it's maximizing functions. Not surprisingly, again, it's slightly different, but in both cases, we have a dichotomy because for cost functions, we have a dichotomy. This is a very deep result, which took about 20, 30 years to find. And was finally, this problem was finally closed in 2017 by Bulatov and Zook. It covers the case of constrained classifiers in the sense that the cost functions can have infinite values. So we know there is an NP hard dichotomy for cost function networks. So this applies to the problem of explanation. So there is a dichotomy. I could spend another half an hour explaining what this dichotomy is, what are the actual function classes which are tractable. But my experience is that, in fact, this is a very beautiful mathematical theoretical result, but in practice, those classes which are actually interesting in practice, which actually occur, are monotone, antitone, or submodular, or supramodular if you're trying to maximize. So, in fact, in the case of Boolean domains, all tractable languages are subsets of the classes monotone, antitone, or submodular. That's when you're in the minimization case. In other words, explaining a positive decision. For explaining negative decision, it would be monotone, antitone, and supramodular. This is for Boolean domains. When you have non-Boolean domains, you get all sorts of interesting new functions, generalizations of submodularity, but frankly, these are unlikely to occur in practice. So what we've seen, the monotone, antitone, and submodular are probably all you're going to get. Okay, so that's to say that we've really, I think, covered all the tractability questions for this problem of finding one explanation. So as a conclusion, so we've seen that there are at least two distinct types of explanation, abductive and contrastive. There are maybe others we haven't even thought of yet. Well, another one which we have thought of is a minimum cardinality explanation, which would be a subset of the features which would be of minimum cardinality. That's another problem which I'll come back to in a second. Explaining a decision is in general co-NP hard, but there are interesting tractable classes of possibly constrained threshold-based classifiers for which one explanation can be found in polynomial time. Monotone, antitone, submodular are the classes that we've identified. It turns out these classes coincide for abductive and contrastive explanations, but not for positive and negative decisions, which is rather surprising. So we have still lots of open problems because we've just been looking at the problem of finding one explanation. What about enumerating in polynomial time all explanations? And again, what about finding a minimum cardinality rather than a subset minimal explanation? Now we know that both are possible in polynomial time for linear classifiers. We're not sure if there's anything else. Recently, we've seen that for monotone classifiers, it's not the case, but there's no polynomial delay algorithm. So I'm not sure what there is left. Perhaps monotone and submodular at the same time. It's really our only hope of finding something more than linear. Okay, well, I think that's all I have to say. I think I can perhaps answer some questions now. Thank you.
Thank you, Martin. Thank you very much. So if anyone has questions, you can ask or you can write them in the chat.
Well, Emiliano?
Yes, so I have a question concerning the connection with the theory of abduction. So I'm thinking about the old paper by Tom Bilander. So they work extensively on complexity of abduction. So the problem of abduction is basically finding an explanation which is a sufficient reason to deduce a certain fact. So the general question, how does it relate your work with the theory of abduction? So mainly to the work by Bilander. And then they have specific results which are very similar to what you have here. So in general, what they show is that finding an explanation in an abduction problem is untractable. I think, if I remember well, they show that is an NP complete problem. So they, at least is NP hard. So they study, I think, problem which are monotonic, and they have a large different classes of abductive problems. So what's the connection between what you are doing and their theory, basically?
Well, that sounds like there's lots of connections. Yes, I didn't see this work before, so if you can send me the
I put it in
the references, that'd be very interesting. I would be surprised if in logic they thought of submodularity, but monotonicity certainly, yes, they probably would have thought of that and found what we found, that it's tractable. But the submodularity is a bit special because it's really only applies. You have a real valued function, which I know that logicians are allergic to real numbers, so they probably didn't even think of that. But yeah, definitely there's definitely some overlap, and I don't claim originality for everything which I've said. Yeah.
Okay, just put the paper in the chat so you can.
I have a question.
Sure.
Okay, so I was wondering, it's a bit surprising because the result about positive and negative explanations, because we know that abductive explanations and contrastive explanations as presented here are dual, especially in the case you presented, because you studied a particular case where you have only two classes, 1 and 0. Yeah. And in that case, the abductive explanations for 1 are exactly the contrastive explanations for 0 and vice versa. So, and then, what is happening with this when you look, I can't see what is exactly the problem when you look for explanations for 1 you don't have the same result as when you look for explanations for zero. It's a bit strange for me, because assume here in the simplest, you have a simple case where you have only 2 classes. So how it will generalize to if you have several?
The problem is the answer, my straightforward answer is that you're asking 2 different questions. You're asking for positive decisions, you're asking tautology. You're asking, is the classifier a tautology? Once I fix certain features, is what remains a tautology? Is this function I obtain by fixing certain features is a tautology? Does it always return 1? Whereas for negative decisions, you're asking, is it always equal to 0? It looks like it's the same problem, but it's not. It's very different. Imagine a DNF. If your classifier is a DNF, it's well known that tautology for DNFs is co-MP complete, but unsat for DNFs is trivial, because you look at the first term and you assign some values which make this term true, and so you've solved your unsat problem straight away. So you can have, depending on which form your classifier comes in, you can have one of these questions, either tautology or unsat is easy and the other is difficult. So I hope that example explains that there is a very big difference in complexity theory between tautology and unsat. Unsat is the same as sat, I mean, it's the same complexity. It's basically, but not unsat and tautology.
And do you think that this result will generalize if you consider, for instance, a non-binary classifiers, in the sense that you have more than 2 classes, so you have different classes?
Well, yes, but yes and no. You'll then be asking, is it true that tau is always equal to some constant c? So that's and then if you don't, so you would have to have, I mean, certain monotonicity would be a good thing, would still work, but some modularity, you would need some modularity and supermodularity. I mean, I think you'll be having to solve the minimization and maximization problem at the same time, so you would end up with fewer classes, but certainly it could be generalized. It's worth looking into. I didn't write down the details, but I think you would end up with fewer tractable classes, but I think monotonicity would be an important one which would still work.
Mm-hmm. Thank you, Martin.
Okay. Any more questions? Okay. Actually, I have a question for Emiliano. The results for abduction, I would assume, have to do with abductive explanation, not contrastive explanations, right?
Okay, can you say again? I didn't hear.
The results that you mentioned from the 90s, I would assume there could be some connection with the abductive explanations, not with contrastive explanations.
No, I mean, what I was referring to is this body of research on abduction. So they have a lot of, so basically abduction, yes. Yeah, they do it in propositional logic. And they have, they have similar properties. They have a monotonic setting, which if you increase the number of features, and then basically if the first was an explanation, then by increasing the number of features, the second one will also be an explanation. So
there is also, even for contrastive, Joao, this notion of contrastive also existed in the past. From these people working on abduction, they used also the idea of contrastive explanations. So the kind of thing you are using here.
Yeah, and then another body of research is probably prime implicance. Prime implicance is closest notion. Well, in prime implicance, you also have the minimality. So that's about another question I had. So you never invoke this minimality condition. For instance, a contrastive explanation has to be minimal, right?
Yes.
Yeah, okay.
That's we say it's a minimal set.
Yeah.
Well, we do make the connection with prime implicants. So it's actually, I think Martin started by saying it's PI explanation, the prime implicant explanation.
Yeah.
Well, if you could send us some references, that would be great, because we would like, of course, there is a lot of bibliography. So if you could send us the references on contrastive, something related with contrastive, we would love to hear about it.
Yeah, I just put a couple of papers in the chat, then I will send you the references. Yeah.
But it's not. I'm not seeing anything in the chat.
Oh, yeah.
Just send it a mail. It's okay.
Yeah, I will send you a mail. Yes. Okay.
Okay, because in the chat there is nothing right now.
Really?
Yes, there is nothing, Emiliano. It doesn't appear.
Okay.
Doesn't matter. It's easy by mail.
No, I think I'm sending to Tom. So sorry. Okay, I'm trying again. Okay, now it is, I think. Yeah. Okay, good. Sorry.
Okay. Okay, very good. Any more questions? Otherwise, we probably can wrap up. No more questions. Okay, so thank you, Martin, for the talk. Thank you, everyone, for the nice questions, and that's it. Thank you very much.
Thank you.
Thank you
for the nice presentation.
Thank you.